Alright, welcome back. Here's another natural circ problem. This is question ID 1692 from thermal hydraulics. And so we're going to use, well, never mind. First thing we do when we look at problems, we look at numbers. Alright, every time. 1.0%. Rated thermal power, 16 degrees Fahrenheit, so that's good. 0.5%. Alright, don't misread that. That's half a percent. And that's it. So we got 2 degrees, 4 degrees, 8 degrees, 10 degrees. Okay, so we're going to have to do some math, right? We know that without even reading the problem. You see that? Now we read the problem. After making sure that there's no number chicanery out there to mess us up. Alright, so now we read the problem. A reactor is shut down with natural circulation core cooling. Okay, key component here. Decay heat generation is equivalent to 1% of rated thermal power. Core differential temperature, delta T, has stabilized at 16 degrees Fahrenheit. When decay heat generation decreases to 0.5% of rated thermal power, core delta T will be approximately 2 degrees, 4 degrees, 8 degrees, or 10 degrees. Okay, so since we're in natural circulation, we know that we're going to have to use some equivalencies. So from our equation sheet, from generic fundamentals, we know that Q dot, or rated thermal power, is proportional to mass flow rate cubed, and that's in natural circ. And we also know that the delta T of the reactor, the difference in temperature between the hot and the cold legs, is going to be proportional to mass flow rate squared. So what these really mean is that Q in state 1 divided by Q in state 2 is going to be equal to mass flow rate in state 1 cubed divided by mass flow rate in state 2 cubed. And that is going to be equal to mass flow rate 1 divided by mass flow rate 2 cubed. Now let's say you forgot your exponents. You don't know how to do exponents. You can't remember what this means. Alright? I would suggest that you put some easy numbers in there and see if they add up. That's a common thing we can do. So this is totally an aside, and I'll put it in red. But you have forgotten that this happens. That this is true. Right? So you go 2 cubed is going to be 8, right? Divided by 4 cubed. You just put in simple numbers, right? So 2 cubed is going to be equal to 2 times 2 times 2, which is 8. And 4 cubed is going to be 64. 4 times 4 is 16, times 4 is 64. That's going to be equal to 1/8. All right? And now you're going to go 2 over 4, and you're going to cube that on your computer. And that's going to equal to 1/2 cubed, and that's going to equal 1/8. So we know that this is correct. We've just proven it. We got nervous during the test and we forgot how to do exponents, or it's been a long time. We want to prove that to ourselves. That's how you do it. Plug in an easy number like 2 and 4 and check yourself to make sure it's right. Okay, so now I'm going to erase that. I've checked myself. I know that this is correct. All right? Where am I going with that? Well, delta T1 divided by delta T2, delta T2 in state 2 is going to be equal to mass flow rate in 1 squared divided by mass flow rate in 2 squared. It's also going to be equal to mass flow rate 1, mass flow rate 2 squared. Got it? So now we have to find this ratio of mass flow rate 1 divided by mass flow rate 2. So what do we have? We have to go up to the blue equation and figure that out. So go back to blue. Mass flow rate 1 divided by mass flow rate of 2 cubed is going to be equal to Q thermal power 1 divided by thermal power 2. Or mass flow rate 1 divided by mass flow rate 2 is going to equal to the cube root of Q1 over Q2. Well, what is the cube root of Q1 over Q2? So mass flow rate of 1 divided by mass flow rate of 2 is going to be equal to the cube root of, well, what's rated thermal power at the beginning? 1% divided by 0.5%. 1 divided by 1/2 is going to equal 2. Alright, so the cube root of 2 is going to be mass flow rate 1 divided by mass flow rate 2. Alright, so what are we looking for in this problem? When decay heat generation decreases to 0.5%, core delta T power will be approximately, alright, it's looking for the second one. It's giving you the first core delta T power. It's looking for the second one. So delta T1 divided by delta T2 is going to be equal to mass flow rate 1 divided by mass flow rate 2 squared. Alright. Now we move things around. Delta T2 is going to equal delta T1 divided by mass flow rate 1 divided by mass flow rate 2 squared. And that's going to be equal to 16 degrees Fahrenheit divided by the cube root of 2 quantity squared. Now, plug that into your equation. It may be easier for you just to do numbers, but whatever, that's fine. I can use my calculator and do this really quick. 16 divided by 2 raised cubed now delete, and that's going to be squared. So I had to use a little fancy finger work. You may have to do this in a couple of steps, but I have a TI-36X Pro, and that gives me a good looking pretty print equation. I'll show you how to do that sometime as soon as I figure out how to hook it up. And that answer is 10.079. That, of course, is going to be in degrees Fahrenheit. Do I have that as one of my answers? I do. So that makes sense, too, right? I mean, we didn't go down from 10 degrees or 16 degrees all the way to 2 degrees, 4 degrees, even 8 degrees by just lowering power by half. And I think intuitively you can get that. So the answer is delta. The correct answer is 10.079, but I think we'll give them a break on our rounding and call it an even 10 degrees Fahrenheit for delta T2 at the 0.5% power. Thank you.